Hi everyone, I am VSCHH from USTC. It is glad to show our work here. We propose TIFace, which aims to improve both tensorial radiance field and implicit surfaces for face reconstruction. Here I will give an overview of my report. Our work consists of two individual pipeline. The TIFace is based on the baseline Tensorial and uses tensorial radiance field for face reconstruction, while the ICCV uses implicit surfaces to reconstruct both accurate geometry and appearance. Novel view synthesis is a core task in 3D vision. In this challenge, given a set of 22 images and poses, we are required to render images from an unseen view using an input pose. Since NERF and its follow-up works have shown great success on modeling a scene as a radiance field and enable photorealistic novel view rendering, we explore its potential in face reconstruction in this challenge. We first try the baseline model Tensorial to address this issue. Tensorial first model the radiance field of a scene as a 4D tensor, then factorize the 4D tensor into multiple compact low-rank tensor components. Though Tensorial achieves fast reconstruction with better rendering quality than previous method, it may not be directly transferable to this challenge. Here we show some example results of the baseline model. Apparently, the reconstructed image contains unexpected floating artifacts and noisy background. We speculate that the interference of the light source in the input image causes this problem. To avoid it, the background pixels need to be identified and filtered out. Therefore, we adopt a SAM-based face segmentation method to obtain high-quality facial mask. In this method, we only need to manually mark a few points as the prompts. Then we use Segment Anything model to obtain a coarse-grained mask. After erosion and dilation on image masks, we obtain the trimap, which can be finally refined to derive the fine-grained mask. However, after we filter out the background pixels, the model still fails in some challenging cases. To avoid this, we propose a novel mask loss for more effective constraints. Specially, we penalize the accumulated density weights on the background to avoid the floating artifacts as shown in the equation. Notably, we also try to use cross-entropy in mask loss, but found that it is not as effective as the proposed loss. Here we show the comparison results of the baseline and our TIFace. The experimental results prove that our TIFace avoid the floating artifacts and achieve better rendering quality than the baseline model. As shown in table, the ablation experiments demonstrate the effectiveness of the proposed mask loss function. Note that in our experiment where we only add a mask, we set the background area to black in order to eliminate artifacts. But the experiment shows that without appropriate constraints on the mask, floating artifacts still exists. To further improve the face rendering quality, we explore another way to render photorealistic faces. Specially, we combine the popular Instant NGP with new S, named it ICCV. Before this, we also tried to combine Instant NGP with NERF, but gave up due to the difficulty of imposing sparse constraints on neural radiance fields to remove artifacts. Based on Instant new S, we adopt a sparsity loss to avoid the floating artifacts. In fact, we observe that the sparsity loss plays a significant role in the final loss function, especially when the model is sensitive to the near and far bound. As shown in ablation results, the proposed sparsity loss avoid most of the floating artifacts, which further improve both geometry and appearance of the rendered images. Here we show the comparison results of Instant NRF and our ICCV. Though Instant NRF may have better rendering quality than our ICCV in some detailed areas, it has unexpected floating artifacts. Since NERF cannot directly impose sparsity constraints, so far we have not found a good solution to avoid this problem. Here we show the example results of our ICCV. Interestingly, although iFace appears to render clearer images, it does not perform as well as TIFace in actual evaluations. In our observation, there is usually a slight color difference between the pictures rendered by iFace and the ground truth. We speculate that the reason may come from the geometric surface that is not completely accurate. Finally, we simply use linear combination to ensemble our models, named TIFace. Compared with the reproduced TensorRF, our TIFace achieves a PSNR performance gain of 2.32 dB in the masked region. By the way, we will open source our code soon, and any questions and suggestions for improvements are welcome. Thanks for your listening.